Hi, I'm Jake Mueller. We did our report on the flags on the moon. So we talked about how when the flag on the moon was placed on the moon, Buzz Aldrin, and as you can see in the picture, had to kind of adjust the flag and work with it to get it into the right position and hold it out so everyone could see it. They, in that time, put a stress on the pole of the flag, and that stress was transferred all the way down to the base of the pole. And so we did our stress analysis on the base of the pole for the flag, and we assumed that they were putting about a total force of about 23 pounds on the pole, and we're then pulling it kind of at a downward angle, and we worked to figure out how much stress was put on the pole and how much that would cause the pole to bend and everything. So we figured that as the astronauts placed the flags on the moon and adjusted those flags, they would cause some stresses to go through the pole of the flag. The flagpole itself was kind of like an L shape. It had like the main support and then also a crossbar to give the flag its shape. Since there's no wind on the moon, it had to have that crossbar to really give it the shape. So we did the stresses as the astronaut was putting the stress on the crossbar, kind of adjusting the flag. We assumed that they were putting about 23 pounds of total force in a three-dimensional direction on the flag. And so we did our stress analysis on how that would transfer down to the base of the flag where it was planted in the ground.
So using various calculations based on the average weight of an astronaut and how much force the normal person applies based on their weight when they're operating at kind of an average capacity, not necessarily the maximum load that they can produce, but kind of just a normal working load that we'd like to work out. We determined a load that on the moon would have been 23 pounds of force. And of course, those are pounds with our earthly gravity measurement. We found the dimensions of the flag, which were 3 feet by 2 feet and 96 inches tall. We assumed the directions of the force, which were contained in a small box, 18 by 9 by 27 inches. Obviously, that's not exact, but those were the numbers that it chose, and that is what it looks like in the image shown. That's what it looks like. Scroll back down to what I got. Anyway, so using that singular force and the direction, we were able to resolve it into X, Y, and Z components, acting at a single point and using the distance that point was from the base. We were able to resolve it into normal forces in the X, Y, and Z direction, and also bending moments.
Okay. So now that we have our general force, we need to break it up into its components in the X, Y, and Z directions. To do so, we need to find both sigma and phi for their angles. So if we go up to our second figure, you can see right there where we have the angles for phi and for theta. So in order to determine those, if we go back down to our equations, we found those using our dimensions that we had given, and we worked out the angles to be 26.57 degrees and 36.7 degrees. So now that we have these two angles, we were able to use formulas to break that force into its different components, giving us 6.147 pounds, negative 12.294 pounds, and negative 18.441 pounds in the X, Y, and Z directions respectively. So now that we have the forces resolved into its components, we need to basically find the applicable moments and their directions as a result from them. In figure 3, we drew out where they were going to be, and from there we had to calculate them.
So after we were able to split up the resultant force into its separate directions and components, we were able to then use these separated component form forces and moments to calculate the resultant stresses, both bending, ordinal, and normal stresses, respectively. We were able to calculate, or what we chose to do was calculate stresses at 2 different points. If you look at figure 3, you can see the 2 points we chose, labeled A and B. At these 2 points, we calculated the
Faisal, there's some kind of feedback.
I'm hearing that too.
Faisal, do you mind try muting yourself while Hunter goes over his stuff?
After splitting the resultant force of 23 pounds, which we estimated earlier, we are now able to use these component form forces to calculate the resultant stresses. And the stresses we calculated were calculated from 2 different points, which are shown in figure 3, labeled A and B. At these points, we calculated the stresses.
So on these points, we were able to calculate the stresses. You said stresses. So you at these 2 points, you were able to calculate the normal stresses, the shear stress, and we calculated normal stress and shear stress using these various equations.
At 2 points that were chosen on the cross section, as seen in figure 3, labeled A and B, we calculated all of the resultant stresses, both normal and shear stresses. At point A, there can be seen a normal stress caused by the force in the z direction and a bending stress due to the moment around the y-axis. And there is a shear stress at point A as well, which was caused by the force in the y direction. Being at the neutral axis would be at its greatest magnitude. And it also had a torsional stress. As well as at point B, there were both normal and bending stresses, although they were acting against each other in this case, by the force in the z direction and a moment around the x-axis respectively. And there was a shear stress at point B caused by the force in the x direction as well as a moment around the z-axis.
So in conclusion, we switched to our modern technology to verify our numbers with our old style handwritten solution. So what we got is our shear stress we found to be comparatively very close. We had 2,134.7 PSI, which was in compression, and our AFEA result told us that is close to 2,200 PSI in compression. Similarly, sigma at point B was calculated to be 1,434.2 PSI, which was in tension. And the AFEA result told us that the value was actually 1,341, which is relatively close. So then for the shear force tau A, which was calculated to be 474.8, and tau at B was calculated to be 472.2, was found to be 572 and 431 from our AFEA analysis. Here is
Authenticity.
yeah, okay. So this one was the tau, right?
Yeah.
Which one was which? This one was the normal stress, right?
Yeah, so
Yep.
the normal stress one has, you see where there's the whole bar on the right side, it says SY, and on the shear one, it says tau, right above the bar on the right. So that's how you can be sure.
Okay. All right. So here is a photo of that was captured on APA using SolidWorks. These are our results for our normal stress at point A and B. And I'll switch to the other one. And this is the photo that was captured for our shear stress at point A and B.
What is this called?
Stress
Resulting.
analysis.
I'll include that in the final production.
What was that?
You can write over me, right? Change my
Just
pocket.
chop it all together, you know, just cut out when he said
Well,
normal
don't worry. I can.
and the other points.
There is a grandiose degree of choppability.
Oh, frick.
And,
Yeah, I didn't time
And you
myself.
know what? You got a voice for radio. You're really good. Faisal, maybe you could say something real quick about why there are differences between FEA and hand calculations.
Dude, I
Just
don't know that.
say,